Our next speaker will be Simon Donaldson from the Simon Center at Stony Brook. In the morning, we heard a little bit about his work in four-dimensional geometry, and now he's going to tell us about dimensions 7 and 8.
Thank you. So the subject I'm going to speak about is not something which I'm, in a sense, really a specialist in. And when we get to the the more detailed results later in the talk, I'll be talking to a very large extent about work of other people. But this is, I think, a very interesting and fascinating area, which I have got some kind of research involvement in. And we were asked in preparing these talks to speak about an area where prospects for progress over the next 5 years or so. And I felt this is an area where that might be appropriate. So I hope to, if possible, explain to you in this talk that there are interesting and hard questions in this topic concerning exceptional holonomy. And what I probably can't really, we probably have no real firm grounds for believing, but perhaps I can't really convey so much, is a belief that actually we may see a substantial advance in our understanding of these problems over that kind of time period. So there'll be two introductory sections in the talk, beginning with one called Joule. So what I'm talking about here are mathematical objects which are sort of special, precious, rare, and which, in a sense, you completely understand and sort of hold in your hand, as you'll see from examples. So an example of what I mean, a classical example, would be the Platonic solids, regular polyhedra, the polyhedra in space with the maximal possible symmetry, where, of course, we have a small list of 5 known to antiquity. And there are no, this is all you get. You don't get any more looking at 3-dimensional regular polyhedra. Another example, somewhat perhaps following on from Jacob Lurie's talk, is to consider, speaking number systems, where technically what I mean here is what would be called normed division algebras, so things satisfying a suitable set of axioms. So there, of course, we have the real numbers, the number line, familiar with, then the complex numbers, which we can think of as the Argand plane. The complex number is specified by a pair of real numbers. And so that's, assuming that's sort of familiar. Then perhaps less familiar, we can go on to a 4-dimensional number system discovered famously by Hamilton in the 19th century, called the Quaternions, which we can think of in different ways. So one way to write them down is we can write any quaternion in terms of 4 real numbers. We have a basis element of the identity, ij and k, where ij and k squared are all -1, and they satisfy this kind of cyclic, similarly, we take cyclic permutations also of this identity holds. So the difference is that these are not commutative. ij is minus ji. Or another description will be to think in terms of the Quaternions as built up of a pair of complex numbers with a suitable multiplication law. We can single out I as being preferred from ij and k, and then write any quaternion as z plus w times j, with z and w as complex numbers. Or a third description, making things more familiar in terms of vector calculus, we think of a quaternion as given by one real number, the coefficient of the identity, and a vector, a three-dimensional vector, and then the multiplication on the vector part is given by a combination of the cross product of vectors and the dot product. So of course, because the identity multiplies in the obvious way. So this law tells you how to define the multiplication for any pair of quaternions. So this forms a four-dimensional number system in the sense that we want to talk about. The difference is that the multiplication is not commutative. But otherwise, you have many of the familiar properties. And then you can go one step further to also discovered in the 19th century. They're called the octonions, an eight-dimensional number system. We won't actually write down the definition of multiplication, but one way of thinking about it is in terms of an octonion is given by a pair of quaternions. So you have 8 coefficients in total with a certain law you could write down for how you multiply these things. So what you lose when you go to this stage is that you also lose associativity. Multiplication is not associative. But we do get, if we take the imaginary quaternions, so we can write any quaternion as the multiple of the identity plus a complementary piece. So if we take the imaginary quaternions, just the complementary pieces, in just the same way as before, if we restrict we take the imaginary component of the product in the quaternions, then we get a cross product on R7, which is analogous, many analogous properties to the ordinary cross product of vectors in R3. Well, we could write down a formula, but for the sake of this talk, there's no real need to do that. In any case, this is an example of what I was saying. This is a complete list of these norm division algebras. There's no other. There's a famous old theorem that there are no other norms of these particular, there are no other number systems in this sense with a suitable precise definition of what we mean. And this is connected to another famous classification result in mathematics, the classification of what's called compact Lie groups, essentially continuous symmetry groups, continuous ways in which you have continuous symmetries of an object. There are 3 families, essentially corresponding to matrices with either real, complex, or quaternion entries. And then there are some exceptional groups, which are connected to these octonions. Because the octonions are associative, you can't just do your familiar algebra kind of in an automatic way. You can't multiply matrices with octonion entries. But some part of what you would do sort of works, and so you do get some exceptional groups, which are sort of a vestige of octonionic algebra, in a sense. So in particular, for what we're going to talk about, we just need to focus on one of these exceptional Lie groups called G2, which is the automorphism group of the imaginary quaternions, or the imaginary octonions, with this cross product. So the invertible linear maps from R7 to R7, which preserve this cross product. So that's turns out to be this exceptional 14-dimensional Lie group G2. So again, there's a famous theorem on the classification of Lie groups, essentially, or you could do a complex version with semi-simple groups, would end up being the same thing. But these are you get complete lists of all the possible groups. You get familiar ones and a few sort of exotic, exceptional things. So now we come to differential geometry. The essential notion we want to recall is that of a what's called technically a torsion-free connection, but let's just say this is a notion of parallel transport of vectors for our purposes. So that's the familiar case of this is when we're talking about working on a sphere, we want to have a rule for how we parallel transport or transport a tangent vector as we move along a path in the sphere. For simplicity, just consider geodesic paths, let's say great circles. Then the rule is that you keep the angle fixed with your great circle you're moving along. So you take your vector here, you move along this great circle keeping a fixed angle. Now we change direction and come down this great circle. So again, we keep the fixed angle, and then we can come back to where we can come back to here, again keeping the same angle, but we get a different vector. So the basic phenomena with parallel transport on a curved space is that you, as you go around a path and come back to the starting point, you'll generally come back with a different vector from the one you started with. So in fact, given one of these connections, we get what's called a holonomy group, which is just given by all the transformations we get on tangent vectors. We take a base point, look at all the loops of that base point. Each loop gives us a transformation of tangent vectors. By composing loops, you see that those things form a group. And so we get a holonomy group of all possible transformations we get by parallel transport. And a famous result in differential geometry, going back to Marcel Berger, is the classification of, again, for this form we'll say the compact holonomy groups, torsion-free connections. And well, there's a special class, a very special class, what's called symmetric spaces. So we'll leave those out. Those are you completely write those down. Apart from that, then again, there are three classical families corresponding to well, the real numbers, the complex numbers, and the quaternions. So the real numbers would be sort of generic case. Complex numbers would be what we correspond to having a complex manifold that's called a Kähler structure, so a differential geometric structure compatible with the complex geometry. And then there are, well, in fact, there are slightly different quaternionic variants of that idea. But for this talk, we want to focus not on these three sort of fairly obvious families or natural families, but there are two special cases which arise connected to these exceptional groups and kind of special phenomena and doing algebraic radioctonians. So there's one case is in 7 dimensions. There's another case in 8 dimensions that we won't, it's very much related to the 7-dimensional one, but we won't actually talk about it any further. Just to say there are analogous questions for everything I'm going to say in 7 dimensions or analogous questions in 8 dimensions. But what is this 7-dimensional case? We're looking at 7-dimensional manifolds with a torsion-free connection with holonomy, this exceptional group G2. That's what we're talking about. So what does this mean? It means we have a manifold. On each tangent space, we have a cross product, modeled algebraically on this standard model. We have a torsion-free connection, a way of transporting tangent vectors along paths, and this should be compatible with the cross product. If you take 2 vectors and multiply them and transport the product, it's the same as transporting them and then multiplying them. So that's just what unwinding the definitions, what this means. Alternatively, you can think about this, it's not quite obvious, but you can think about this in terms of these structures are given by Riemannian metrics on a 7-manifold with a special property, a special class of Riemannian metrics. That's because any Riemannian metric has what's called a Levi-Civita connection associated with it. And so the connections we're looking at always arise in that way. So we can think of another way point of view, we're studying a particular branch of Riemannian geometry. So these structures, these G2 structures, I mean, we might think of them as a sort of a rather recondite area in differential geometry, but they are, I mean, on the other hand, maybe they're what we're all made of. Maybe they're the structure of the universe. There is M theory, which I know almost nothing about beyond what I've written, but anyway, these G2 structures are the fundamental idea in this. The idea would be that space-time is really 11-dimensional, the 4 visible dimensions and the sort of tiny dimensions given by a manifold with one of these G2 structures. So there is, there's a lot of mathematical motivation for studying these things because they're very kind of, as you said, very special, beautiful things. If you classify everything, you've only got these possibilities. But there is also motivation from physics because possibly you're studying the structure of the universe. But I mean, maybe not, but never, we don't really. No. So second section, this is a bit shorter. This is also very general. So what I want to talk about is partial differential equations. I think most people are mathematicians, so I'm going to be telling you what you all know. So what I'm going to say is everything in the world, almost everything, to be safe, can be described by a partial differential equation. So for example, the oldest case would be Newtonian gravity. I thought I should write down an actual differential equation, so that's why I put that. So that would be in terms of the gravitational, the matter density and the gravitational potential. This is the Laplace operator, of course, or Maxwell's equations, or the Schrödinger equation, or fluid mechanics. Possibly, maybe there's some possible reasons to doubt whether this is actually a precise model of fluid dynamics. Or closer to what we're going to talk about, perhaps would be think about the minimal surface equation, the equation which determines the shape of a soap film, as illustrated. So I mean, we can take a soap spanning some kind of wire, it takes up some kind of shape. What shape is determined by solving a partial differential equation? I'm telling you what you all know. So the point is that these things are the kind of opposite of joules. They're everywhere. Everything is a partial differential equation. It'd be impossible to say everything about partial differential equations because they're everything and they're much too big. But so I mean, conversely, if we have a partial differential equation which just comes from somewhere, not necessarily from any kind of real-world application, we can study it. The solutions may do something interesting, say something bad. So it kind of makes sense. There's a whole world in this differential equation, even though it's not necessarily actually a real world. So a whole new world to explore. So what does this kind of obvious remarks have to do with the first section? The point is that finding one of these G2 structures on a 7-dimensional manifold is solving a PDE. I'm not going to write it down, but if you set it all up, then you find you have to solve a PDE for something. You can set it up as a PDE for a 2-form, and then what you would get would be a kind of a nonlinear version of the Poisson equation. You get a partial differential equation whose linearization would involve this Laplace operator, but there'd be lots of nonlinear terms which you could hardly even write down in an explicit way. Probably not easy to write down in a very explicit way. But there's not just these structures themselves, there are also interesting things we can look at, interesting geometry we can look at in a G2 manifold. There are a particular kind, something called associative submanifolds, which they're special forms of minimal submanifolds, so higher dimensional generalizations of the minimal surfaces. They're just defined by saying that their tangent space is closed under the cross product operation that we're supposed to have. But also, in a similar vein, there are special solutions of the Yang-Mills equations, which are nonlinear versions of Maxwell's equations, also involving the notion of parallel transport, but not just of tangent vectors, but of more general objects. So we have all we want to study the G2 structures themselves, and these kind of auxiliary objects in one of these G2 manifolds, and all of these things are solving partial differential equations. That's the point I'm making in this section. So that's our kind of preliminary, that's the introduction. What are the prospects in, what could we'd like to know about these things? What can we say more? Well, one thing to say is that the topology in question is sort of well understood, well, at least sort of interpreted, is at least in good cases, is well understood. If you recall, if we just think about the topology of surfaces, say orientable surfaces, we can make these by taking the connected sum of copies of the torus, this connected sum operation is indicated here. And if we restrict to the case of, it's called two-connected seven-dimensional manifolds, which is an interesting, it's a subclass, but interesting subclass for these purposes, then there's a similar topological statement where but our building blocks would, well, they'd be more or less the product of S3 times S4, but actually you need to allow a kind of a twisted product. In the same way as if you were doing non-orientable surfaces, you might want to allow Klein-Bottle summands, which are kind of twisted versions of a torus. This is in fact, more technically, people to know, this is what involving the Pontryagin class of the seven manifolds. But anyway, at least in many cases of interest, you can write down, you have a complete control of the topology of the manifolds you want to consider. And what is the state of knowledge? There are large lists, many thousands long, of cases where these structures have been constructed. Initially through work of Dominic Joyce in the 1990s, a later kind of construction of Alexei Kovalev, which was generalized more recently by Corti, Haskins, Passini, and Nordstrom. So the upshot is you get huge numbers of examples in which various phenomena can be displayed, such as, for example, two-connected examples. But there's no kind of systematic existence theory. These examples, the way they all come from what's called gluing constructions, so where you can take two things that you know with something of a simpler geometry, glue them together to get an approximate solution of the equations, and then use some sort of analysis argument to deform to an exact solution. So with ingenuity, people produce examples, but there's no kind of systematic understanding. So let's just start it. If you just gave me a seven manifold, chances are you'd have no idea whether it had one of these. You'd have no idea one way or the other whether it had one of these G2 structures. But if you did happen to know it had one, then another interesting problem arises that these structures come in fine-dimensional family or moduli, similar to I call it T, analogous to the Teichmuller space of a Riemann surface. So there's a whole manifold, T, parameterizing these structures. There's also a period map, which maps T to the third cohomology of your manifold, which is a local homeomorphism or diffeomorphism. So locally, the moduli space is identified with the third cohomology of the manifold by this period construction. So this is a bit more technical. You can put together the metric and the cross product. So the metric, you identify the tangent space with its dual, so you can regard the cross product as a three-form. The condition, this torsion-free condition says it's a closed three-form, and then this period map is simply to take the class of this closed three-form in the Durham cohomology, for those who know about that. So it's relatively easy to prove. This gives a local, complete local invariant of the structure as we make deformations. But again, if we go beyond that, then the basic questions that we ask, which we know almost very little about. I mean, is this moduli space connected? Could there be two completely different components? Is this period map globally an embedding? How can we, supposing it was, what would the image be in the three-dimensional cohomology? So all these are the basic questions which, so essentially nothing really is known about in any general way. What kind of mathematics is relevant to understanding these questions? Certainly, the convergence theory in Riemannian geometry is very relevant. If we imagine we wanted to understand the boundary of this image of this domain P, so we want to take a sequence of these structures and say what could happen in the limit, speaking. So we can think of this in terms of Riemannian metrics, as I said. And so we're in a situation we'd like to understand what can we say about the limit of this sequence of Riemannian manifolds. And there's a whole theory of such questions. One can start with the notion of a Gromov-Hausdorff limit, which is a very sort of a coarse notion. and then perhaps go on to refine that to consider G2 space, not manifolds, but G2 spaces with singularities. And there are results in this direction of Chiga, Kolding, and Tian. So certainly some things are known, but nothing, essentially nothing in detail is known about the singularities that would arise, that would enable one to get any kind of precise answer to your questions about what the boundary of this period domain is at present. There's a large gap between we do know something, what we'd like to know was kind of a big gap. Similarly, these other objects, so say the associative submanifolds and these special solutions of the Yang-Mills equation, they're interesting in their own right, but they could also shed light on these questions that we've raised about understanding the moduli. One direction, we could hope to define a kind of an enumerative theory of these things. So to define a notion of counting associative submanifolds, perhaps in a given homology class, say, to arrive at a number that will be an invariant under continuous deformations of our G2 structure. So this would be similar, if you could do this, this would be similar in spirit to the well-known cases of Gromov-Witten invariants in symplectic manifolds, where one counts holomorphic curves, or of the invariance of four manifolds defined by counting Yang-Mills instantons or Seiberg-Witten solutions, or similar things. Or in terms of this periods, one could think, supposing the standard observation that if we take the volume of one of these associative submanifolds, it's just given by the integral of the free form, phi, so it's entirely homological object. It's given by the pairing of this period point with the homology class of our associative submanifold. So if we knew, if we had supposing we have our G2 structure and we know we have an associative submanifold in some homology class, supposing we knew as we deformed our structure, we always had an associative submanifold in this homology class, then we would know that we always had to satisfy this constraint that the pairing in homology between the period point and this homology class of thing would have to be positive by this observation, because our associative submanifold has got a positive volume. And we'd expect that, the picture we'd expect as we approach the boundary of P, we might have a case where this would go down to 0 because our associative cycle is sort of shrinking down to a point. So, potentially, all of these things can sort of tie together. One might start to understand what's going on. But, I say, interesting phenomena. I mean, so I'm saying this is a kind of a picture, a dream, you might say, that we're going to have, many people have. But interesting phenomena and very large difficulties arise. Basically, we don't understand the PDE well enough to be able to actually do any of this rigorously, or even to know whether it's a well-founded idea, whether even one should expect to be doing this in 20 years' time, or whether there's sort of fundamental obstacles to doing this, whether maybe it's too naive. For example, one kind of phenomena, this is work of Johannes Nordström. One kind of phenomena that occurs is that supposing we have a pair of associative submanifolds. So those are three-dimensional things in a seven-dimensional manifold. So we don't expect that they intersect. But if we want to consider families, if we have a one-parameter family of these structures, things will move around. So we expect that generically they might intersect in a one-parameter family. So it's like this picture in lower dimensions of a pair of curves in space which don't intersect. In a one-parameter family, we can imagine changing from this picture to that picture, changing a crossing like that. So what happens, as Nordström explains, is that when in such a situation, what happens is that when you make this crossing, a completely new associative submanifold is born in the homology class of the connected sum, indicated by this L0 here. Well, it could be either a new thing is born or an old thing dies. You can't really tell which one. But anyway, the naive idea of counting the associative submanifolds is not going to work because something drastic is going to change when you go through such a crossing phenomena. So this is the kind of thing, the kind of new structure that you see essentially by studying these differential equations, which has to be taken into account in a putative theory along these lines. So that's really all I have to say. So I say a complete understanding of all these things, a complete understanding of how you can take limits of these G2 structures or limits of families of associative submanifolds, all these things, that really seems a long way off because, as Brian White was explaining today, but if we look at minimal submanifolds in high codimension, not codimension 1, then there's very little theory one can appeal to understand these things. But nevertheless, I think although it may not be possible to have a kind of a complete final word on these things in the immediate future, I have a feeling that we're at a point where a lot of progress will be made in the next 5 years, at least in understanding in more detail what should happen, and perhaps getting a picture of what ought to be true and should be possible. So I think it's an exciting subject to think about.
We have time for maybe 1 or 2 questions. Yeah.
Does one of Milner's exotic 7 spheres, the 3-sphere bundle over the 4-sphere, does that appear in any way in these G2 manifolds?
Well, it does. So actually, I oversimplified in my account because when you take account of the differential topology, you could take the connected sum with an exotic sphere. So there's a kind of a more refined classification of the smooth structure involving the Z28 of. But that has been completely analyzed by again Nordstrom and Crowley recently, and examples where you have interesting examples of having different smooth structures with different a same topological manifold with different smooth structures having G2 structures has been discovered. So it does very much interact with those things. In fact, that's one of the attractive things for me is that I'm basically a low-dimensional person. So we always say, oh, well, high dimensions, the topology is all understood, everyone knows. But kind of all that beautiful topology is not often applied to actual problems. So here is a situation where one can really apply the understanding from the 1960s and 70s of high-dimensional manifold topology in very explicit examples. And that's an attractive feature to my mind.
So the moduli spaces for different kinds of compact Kähler manifolds can be described in terms of homogeneous projective varieties. How does the moduli space for G2 structures, what do they look like? The moduli spaces.
Well, that's what we don't know. I mean, this theory of periods is very much analogous to similar theories in algebraic geometry, but it's somehow, we don't have algebraic geometry to appeal to. So there are beyond what I said, nothing is really known. There's a local picture, but nothing, so the local picture would involve, well, just the Grassmannian of, it is just the homology, it is just very simple. It is just this H3, but there's no kind of global understanding, really.
You told us there are thousands of families of these G2 manifolds, and they have all more or less the same topology, yeah, and it's similar to what happens for Calabi 3-folds. If you consider conifold transitions, you have mild street conjectures. It's essentially only one modular space. Did people speculate that maybe different manifolds belong to the same family, or one can make maybe some extensional problem with just one modular space?
That could well be possible. Yeah, there could be some analog of that. Maybe that's the point to say that a lot of this geometry is where we can say very analogous things in Calabi-Yau geometry, where we have a much better understanding because we have the algebra to So it's,
No, but there are conical transitions, and you go through non-algebraic varieties,
Yeah.
which you get someone.
Yeah. and certainly you can
Yeah.
make analogous
And also this
deformations.
wall crossing happens in kind of non-controlled way. I don't know, homologically, when two Lagrangian, two associative manifolds intersect, it's kind of differential geometric information or topologically, as I understand. Yeah.
There's no control that
Yeah.
that's exactly.
I see.
There's no way that we know of controlling
I
it.
see.
Maybe we have time for one more question. Is there any other, or no questions? We're done? All right, one last one.
So you say it's reasonable to hope for significant progress. So what makes you optimistic?
Well, I said I couldn't really give you any I just feel that there has been a lot of progress in the last few years. So I think it's partly perhaps because more people are working on them. These questions have been around, many of them, for 10 or 20 years, but somehow they've come more into the limelight recently, and so there has been a lot of work, a lot of progress, and I think maybe it's my hunch that progress will go on.
Okay, thanks.